All right, uh, let's get started. Uh,
Yes, sir.
Hello, everyone. Good evening. Thanks for joining.
Good evening, sir.
Uh, Today, so I will be hosting this conduction and convection heat transfer problem solving sessions. What we usually do is this session contains like 2 hours, and what we usually do is we solve some problems for let's say like 40 minutes or maybe 1 hour maximum, and I will leave another 1 hour uh, for so that you can, if you have any questions, you can ask me, and if you have any doubts, you can clarify them. If you have any new questions you came up with, and if you want any solutions for it, I will be happy to solve in front of you. So all these activities we can do in 1 hour, and the other hour we will be solving some uh, few questions, few problems we will be solving, which should be helpful for you to solve your assignment problems. So that's the main focus of these sessions. And usually we will start like 7:02 because I give like 2 minutes buffer so that if some students have any connection issues, they will be able to join. So usually we will start our sessions on 7 to every Saturdays around 7 2 p.m. and uh, yeah, it will be for 12 weeks. And there is also one more session. Feel free to attend that also. There also we will be solving some more questions. These things will give you practice to solve heat transfer problems, and which will ultimately enable you to score very high marks in your exams, and also in general understanding heat transfer concepts. That is something about this course. Um, so, a little bit about me. I'm a PhD student at IIT Gandhinagar. I'm very happy for Professor Suman Chakraborty for agreeing me to take this problem solving sessions. I acknowledge him. And so I will be hosting one of the session. As I said, there will be one more student who will be hosting the other session. I think that is on Tuesday. Okay, please feel free to attend that. And my research work, so I'm basically like a final year student, and my research work is related to rocket propulsion, CFD, and multi-phase flows, dynamics, and modeling. All it involves a lot of high-level complex physics, but the basics always comes from heat transfer and fluid mechanics, and uh, that's why if you have fundamental knowledge from fluid mechanics and heat transfer, you can tackle any problems. Also thermodynamics, you can tackle any problems in mechanical engineering or aerospace engineering or even chemical engineering. So in that way, it is a very good course. I'm very happy that these many people are taking, and I also encourage everyone to attend all the sessions. And if you have, whenever you have any questions, you can stop me at any time, and you can ask those questions. Um, so how we designed this weekly session is, so we expect you to complete the first week or every week's video. We expect you to look at the lectures, understand the videos, and if you have any doubts with that, you can come and ask me. uh, so if it is a week one, we expect you to complete the week one lecture videos. Even though if it is, if you haven't, it's fine, you can still come and attend. I will give you a brief introduction about what we did in every week, and we will go forward with it. But it would be very good, and it would be very supportive if you have completed those lecture videos. Nevertheless, the first week is introductory, and I hope probably like everyone would have already known certain concepts. These are 12th standard or 10th standard concepts that we usually begin with, right? So conduction, convection, we already know. So in this week, what we studied was conduction, and a general introduction of conduction. It's not yet it's not yet complete. So we studied like steady state heat conduction, and also if you have if you have a temperature field which is varying with respect to space and time, then you have to solve something like conduction equation or heat equation or energy equation. So all these are same equations. So in general, we call it energy equation. If you make an assumption that only heat fluxes only due to conduction, then you becomes a conduction equation. And we saw like internal energy form, and we also saw a specific heat form of the equation. Um, Although we didn't go in depth of those equations, which will be covered in the subsequent lectures, today's problem we will mostly go through the conduction and a little bit of convection. Okay, so the problems that I'm going to deal today is going to be on conduction and convection. And uh, so before I begin, if you have any questions regarding the uh, lecture materials, you feel free to ask. If not, we will go forward with the problem solving. And this is supposed to be an interactive session, so feel free to stop me anytime. You can unmute yourself, or you can even switch on your cameras. It will be very interesting thing. So and you feel free to ask any question anytime. Okay, so I encourage you to ask any questions anytime. All right. So maybe I will pause here for 1 or 2 minutes so that if you have any questions, please ask me. You can also use this chats in the Google Meet, and you can ask your questions there also. But I would actually encourage you if you could unmute yourself and ask.
Good evening, sir.
Good evening, Unnati ji.
Sir, are there any lecture notes provided? Because I have some doubt in derivation of CP form equation.
Okay.
So, I missed something in between,
Mm-hmm.
but I didn't get it after watching the video again. So,
Okay.
are there any notes?
So, you can follow books. We do not have lecture notes. It's just the videos, and you should take notes while watching the video. Um, but what you can do is you feel free to share it with me, the derivation, or you feel free to ask if you have any doubts during the derivation. You can let me know, and I'll be happy to help. Where were you exactly stuck?
Okay, wait a minute, sir.
So probably maybe I also went through the lectures. This is the CP equation that we have.
Yes, sir. The equation marked in box just
Mm-hmm.
above that there is a term beta.
Uh-huh. Yeah.
That term I am confused in that term.
Okay. So you were not able to get this term, or is it
Yeah.
okay?
Uh, can I get this PDF or can I take some screenshot from the beginning?
Yeah, you can take. So what I will do is maybe it may not be the interest of other students. What we will do is we will finish all the problems today, and then I will again come back to this question, and I will show you how this term will come, and if you have any doubts you can ask me later. Is it fine?
Okay, sure, sir. Sure.
Okay, so let's complete then today's problems. I have like 5 problems today. Actually I have 6, but if possible we will solve the sixth one. um, if not, we will solve it in the next session. So because the sixth one requires a little bit about energy equation, which was briefly which even though professor derived, um, it's not yet completely, he didn't give full picture till the first week videos, so we should go through the second week videos also. Nevertheless, let's get started. If there are no more questions, let me quickly check whether my recordings are going on. Okay. And by the way, this also will be recorded and will be posted in the YouTube. And the links also will be shared with you by NPTEL, so you no need to worry if you miss. But because of it will be posted, don't be like I will look at the YouTube video. Please come and attend this session. Okay. All right. Um, so let's get started with the today's questions. The first question is a simple thermal heat conduction problem. So these are, so first few questions are like warm-up questions, so it is not really very difficult questions, but these are the questions being asked in the assignment also, so it should be very easy for you guys. Let me go through this question. um, a plane wall has a thermal conductivity of 2 watts per watt per meter Kelvin, and if the inner surface is at 1100 degrees Celsius and the outer surface is at 350 degrees Celsius, then what should be the design thickness of the wall to maintain a steady heat flux of 2500 watt per meter square? Okay, so it's a very simple question. um, Let me draw a simple plane wall so that you will get an idea what this question is about. So this is like a simple plane wall. Okay, and let's consider this as a inner side and this is outer. Okay, and what has been said is you have inner side, let's say Ti, and maybe outer I will call it To. Okay, and what they are telling is this plane wall has a thermal conductivity of 2 watt per meter Kelvin, and the inner surface is at 1100 degree Celsius. Okay, and the outer surface is at 350 degrees Celsius. So what they are asking is, let's say my heat flux is, if it's a steady heat flux, please note that this is a steady heat flux. If my heat flux is we are denoting it as small q double prime. Double prime means per unit area. Okay, which we usually use it for flux. This is the notation we usually use it for fluxes. So for heat flux, this would be 2500 watt per meter square. If we have this steady heat flux, what should be my delta x, or what should be my thickness? Let's say I call it L, or you can call it T. What should be this thickness is what they are asking. Um, and uh, so let's write down some of the assumptions. What are the assumptions that we are going to take here is, it's a steady heat flux, or it's in steady state condition, which means it is the profile is fully generated, it is not dependent on time. That is what it means. The dependency of temperature field with respect to time is not there, which means t is not a function of time. T is not a function of time. T is only a function of space. That is what it means. It can be x, y, and z, but here we are going to talk about planar wall, which means we are going to ignore the y and z axis. So t is a function of just x. That is what it means. Okay, and we are taking thermal conductivity to be constant. So we are also telling it's a constant properties or constant transport properties. Okay, these are some of the assumptions I'm just giving you because it's good to understand what are the assumptions. Sometimes we uh, typically okay, this is a heat conduction problem, we'll just write q is equal to minus k dt by dx and then we'll try to solve. Although for this problem it is that trivial, you can just solve it, but it is good to understand at what conditions these are applicable. So basically when we do that, we are making such assumptions such as it's a steady state and it's a constant properties, and you will understand the implication of these assumptions when you solve when you use the equation, when you use the conduction equation that you derived in both internal energy and CP form. uh, when you use those equation to solve some problems, uh, you will make these assumptions and then only we will be able to remove certain terms and then we'll be able to solve. So that's the reason it's good idea to understand what are the assumptions that we are making here. Okay, so the first in this these are the two assumptions, main assumptions that we are making. uh, um, Other than that, I think you all know what to do now, right? So we have some heat flux which is going from high temperature to low temperature. Here its inner wall is at high temperature, outer wall is at low temperature. So heat is flowing from inner wall to outer wall, and the flow is going to be conduction. Okay, and if that is conduction, we will use Fourier's law of heat conduction. Fourier's law of heat conduction. So what does Fourier's law of heat conduction says? Let's say this is, in the x direction. We can say Qx, or heat flux, is nothing but minus k Tt by Tx. That is what Fourier's law of heat conduction says. Now, here we are interested in the total thickness of the wall, so we can replace with the derivatives to be delta t and delta x. So when we do that, what happens? Minus k delta t by delta x, where the heat is flowing from, so this is something you need to understand. The heat is flowing in this direction. Okay, so there is a temperature gradient along the x-axis. So whatever the delta x that you take should be the x-axis limit, or in this case it's a thickness. Okay, and the delta t here, what should be the delta t here? So let's say if I want to write delta t in terms of Ti and To, what should be the delta t? So will it be Ti minus To or To minus Ti?
TO minus TI.
Okay, why not it should be Ti minus To?
Because minus is given, no?
Already
It is
given.
like that.
Exactly. Very nice. So, and also, if you look at it, we are taking temperature gradient. So, when you
Yes.
use a temperature gradient, we always go, the the right hand side, or the right, so along the positive x, whichever is maximum x minus the minimum x, that's what we do. This is a gradient, right? So in that way it's To minus Ti. Okay, and also, let's say if you are confused, let's say, I do not understand why it should not be Ti. You think about it. If it is Ti minus To, Ti minus To would be positive quantity, and K is already positive. So Qx would become negative quantity. And if Qx is negative, we already know heat flux is a vector. It comes with the direction. If Qx is negative, which means heat is flowing in the negative direction. But that is not the case in our uh, scenario. The heat is going from in the positive direction. It goes from high temperature to low temperature. So heat is flowing in the positive direction, and if the heat is flowing in the positive direction, Q double prime x should be positive, and if that should be positive, then this should be Ti minus T. So this is just a another way to ensure that you understand it right. But in general, in principle, the rightmost node you need to take first, and then you need to subtract it with the left node. Okay, so in this case, it is To minus Ti. All right. Um, so let's say if we substitute all these things, we have K is 2. So minus 2 into T naught is 350 degrees Celsius minus 100 or 1100 degrees Celsius. Okay. Divided by the thickness L, or delta X, is what we are planning to find. Okay. And the heat flux is also given Q double prime X. Here it is Q double prime X, which is also 2500 watts per meter square. Now what you have to do is you just need to rearrange. Um, um, so 1100 minus 350, how much is the L coming out to be? If you guys find out, please let me know. So I think this delta T is around 750,
So,
right? So you can write this as 2 into 750 divided by 2500. So how much is this coming out to be? So I'm getting something like 0.6 meters. So I hope all of you are like, you know, must be in the bachelor's, must have already been taken heat transfer or taking heat transfer. So which means you already have basic concepts of calculus and, other uh, uh, basic, probably you must have taken fluid mechanics and also mathematics, basic calculus. Those two things are necessary for this course. So that's why I'm not giving much importance through these calculations. But the only thing you need to understand is where the heat flux is going, and what should be the sign of delta t that we need to take, and what should be the delta x, the length that we need to understand. Okay, in this problem, luckily we do not need to worry about the area across which the heat is flowing, because everything is in per unit area basis in this problem. But in future problems we may need to understand which area is necessary. Usually while we solve heat transfer problems, um, sometimes we get uh, confused, or sometimes I get confused, if not you, like which area to take, right, for the heat transfer to happen. So based on that, your answers will vary and you might lose marks in terms of thing. And also, you know, so for that you need to understand, it comes with the practice. Only if you understand the problem correctly, you will be able to identify across which the heat flux is flowing, and how to find the area of the heat transfer. Okay. All right. I think first question is there. If there are any questions, please stop me. You no need to wait for me to complete the problem. You can stop me at any point and you can ask your questions. Um, I hope there is no uh, doubts in first question. If not, feel free to ask. So if there are no questions, let me move on to the second question. So this is also like warm-up question. You guys must have already know. Uh, let's see what this question says about. There is a back surface of a plate which is heated at a rate of 100 watts per meter square. So there is a plate, and the plate's back surface is heated at 100 watts per meter square, and the front surface is cooled by airflow at 30 degrees Celsius. It is given that heat transfer coefficient between air and the plate surface is 50 watt per meter square degrees Celsius. Considering steady state heat transfer, what is the temperature of the front surface of the plate? Okay, so it's basically, you have a plate. Let's say, how can I draw the plate? Maybe I will draw in a horizontal direction now. So this is the plate. The back surface of the plate, you are heating it. So what is the, maybe I will draw this as y direction. So Qy is 100 watts per meter square. And in the top surface you have air, which is going to cool the surface of the plate. And you have air whose temperature, let's call it T infinity, which is 30 degrees Celsius, and you have air flowing. Air can flow however it wants, but it cools down the top surface of the plate. So if that is the case, what they are asking is, what is this surface temperature? Ts is, okay. And what they also gave is, they gave, what is it? They gave H to be 50 watt per meter square degrees Celsius. Okay. So again, you can write down the assumptions. So assumptions will be steady state heat transfer, and also constant convective heat transfer coefficient. That is one of the assumptions that we are making. And plate is uniformly heated. That is one more assumption. Okay, the plate is the bottom surface of the plate is uniformly heated with 100 watts per meter square. Okay, maybe I will write it down one more time here. The steady state uniform heating. So if the plate is not heated uniformly, what do you expect to happen? So we have 100 watt per meter square at the bottom surface of the plate, right? So I am telling it is uniformly heated. Let's say it is not uniformly heated. Let's say I have, this is the x direction. I have heat flux varying at x direction. What would happen? What do you expect to happen? What else will be a function of x direction? Okay, there's a big silence. So what I'm trying to say is the heat flux is going to vary along the x direction. If that is the case, the heat conduction inside the plate, plate also has some thickness. So when the heat enters the back surface of the plate, it has to go through the front surface. If the only way it can go through is through conduction, and this conduction heat flux, we know that heat flux is perpendicular to the surface. So if that is the case, the conductive heat flux here, the conductive heat flux which is going to go through this plate will also be a function of x, will also vary along the x. Okay, if the conductive heat flux vary along the x, that is the heat flux which is getting carried out by convection by air, right? So if that is the case, the temperature, top surface temperature Ts we have, will not be a one value. Now it will be a function of x, because the heat flux is continuously varying along the x. So the temperature, surface temperature also varies along the x, and also the internal temperature of this plate. If you have, let's say, at some point in the middle of the plate, if you want to find the temperature, that also will be varying along the x. That is one complication that we will have if you have non-uniformity. Okay, so uh, that is something, but here it is not the case. We can come back to the problem. So what we have here, we we have to find the surface temperature. So how do we find it? Any idea? So the hint is already here. We have already given heat transfer coefficient. Okay, um, if which means the air is going to take away the heat, which means the mode of heat transfer here is convection. Okay, and if it is convection, we all know there's a law called Newton's law of cooling. And what does Newton's law of cooling says? The heat flux is nothing but h time surface area of the heat transfer, or if it's a heat flux, then you do not have area here. H times Ts minus T infinity. We need to find Ts. H is given, heat flux is given, and T infinity is also given. So we just need to find Ts here. Is this clear? Why didn't we use conduction? We use convection formula here. I hope it is clear. If not, please let me know. I can repeat. Okay. So if this is the case, we have 100 watts per meter square, which is equal to H is 50, and Ts is what we need to find, minus T infinity is 30 degrees Celsius. Okay. If this is the case, what happens? 1, 2, Ts is nothing but 30 plus 2 is equal to 32 degrees Celsius. Okay, this is what we are supposed to find. So if you change the heat flux, if you increase the heat flux, the surface temperature is going to increase, right? So if I increase the heat flux to 200, what happens is the temperature becomes 34 degrees Celsius, which makes sense. If you have higher heat flux coming out, then the plate would be very hot. So which means 32 will become 34. That is what it means. Okay. All right. I hope this is also clear. This is, again, direct application of uh, conduction and convection formulas. If there are any doubt, please let me know. If not, I'm moving on to the third question that we have here. Third question is a little bit different. We haven't did this in the, we have discussed a little bit in the lectures. Professor used to say that K, you can take isotropic, and uh, you can take it to be constant, and you can solve it. But here it's something different. Okay, this is um, and this is more representing the reality. In reality, you cannot take thermal conductivity to be constant. Let's say if you're once you graduate from your engineering, let's say if you enter into some industry and you are expected to do some heat transfer analysis, at that time you cannot put thermal conductivity equal to constant. It will be very nice to solve in the problem because it will be very easy, but in reality that is not the case. Thermal conductivity varies with temperature, and it is sometimes it increases, sometimes it decreases. We also saw that for different materials it behaves differently. Here I'm taking a more general case. Okay, so what this case says is to determine the effect of temperature dependence on the thermal conductivity on the temperature distribution in a solid. Let's say if you have a solid and if you are heating, or it is subjected to a different temperature gradients. Now if that solid has some it is going to have some thermal conductivity, and if that solid has a thermal conductivity which is a function of temperature, then how the temperature distribution within the solid is going to vary. That is the question basically. So consider a material for which this dependence may be represented as K is to be some constant K naught plus A times T. A is some coefficient times temperature. T is temperature. So K naught is positive and A is a coefficient that could be positive or negative. If it is positive, it is a thermal conductivity is going to increase with increasing temperature, which is basically for the gases. For gases, typically we have thermal conductivity increasing with temperature. Okay, or it can also be negative. If it is negative, which means thermal conductivity will continuously decrease with temperature. Sketch the steady state temperature distribution associated with heat transfer in a plane wall for three cases corresponding to A positive, A equal to 0 and A negative. A equal to 0 is the very easiest case, and we will be very happy to solve that case because it doesn't involve much thinking. But if A is positive and A is negative, how would the temperature distribution within the plane wall? Here we are going to consider plane wall, which means one dimension. We are going to restrict our uh, problem into one dimension. Then how does temperature vary along X? Whether it will be a straight line, whether it will be a different curves is what we are going to find out. Okay. I hope the question is clear. So if not, maybe if I draw the diagram again, it would be very clear. Again, this is a plane wall. Okay. And let's say this is the X direction. And let's say this side the temperature is T1 and this side the temperature is T2. Okay, and you have, yeah, basically this is the X direction. Maybe I will put it like this, X direction. So we know that temperature is going to be a function of X in this. So let's say if I have a heat flux coming Q double prime X, let's say when I have heat flux coming in, this is going to be steady state. Again, we are going to make this assumption of steady state. In steady state, what happens? The heat flux remains constant. Heat flux is basically constant, and it will be same for every section of the plane wall. So for every section of the plane wall, the heat flux will remain same. That is what, or it is not dependent on uh, uh, sorry, heat flux. Steady state means heat flux is it's not a function of time. And also if it's a plane wall, it is going to be we are going to make assumption that it is not two dimensional, it is only one dimensional. The heat flux is going in only one direction, and if that is the case, we do not have any heat generation, which means every section will have same heat flux. Okay, which means basically the heat flux Q double prime X is a constant. Okay, let me write that down also, which is the case that we saw till now in the last two problems also. Q double prime X is a constant. Last problem was Q double prime Y is 100 watts per meter square. In this problem, it was like 2500 watts per meter square. It is not varying with respect to X or something. So this problem also, we are going to make that assumption. Okay. And the temperature is, again, we are doing only one dimension, so temperature is a function of x only. Now the question is, you have thermal conductivity which is k naught plus at, and a could be either 0 or positive or negative. Okay, all these three cases, if these are the three cases, how will be this temperature distribution is what we need to sketch. Okay, which means, let's say if I draw this diagram in terms of x and t graph. Okay, you have t1 here, you have t2 here, this is 0 and this is some L. Okay, so let's say this distance is L. So how will the temperature vary is the question. Whether it varies linearly, whether it is vary like this, how it will vary is the question. Okay, so do you have any idea how we can proceed with this?
I think linear.
For which case? We have three cases. We have a equal to 0, a greater than 0, and a less than 0. So let's say I will take a case first.
Is equal to 0.
Yeah, let's say if you take case a equal to 0,
Yeah.
what would happen?
K is equal to K0.
K equal to k0. So how would the temperature profile look, or how will you proceed with this?
K is equal to K0.
How will you find the temperature profile? So your answer is actually right. It will vary linear,
Yeah.
but how did you come to that conclusion?
I think it will be at the origin.
Uh, can you come again? It will be at the on origin. What happens?
Yeah, yeah, yeah. It will represent at the origin.
Okay, it varies like this. Is that what you're telling?
K is equal to K0.
So okay, one more thing is, you can one thing you can one thing we can also write is, this is 0 and this is L, right? So temperature at x is equal to 0 is known. Temperature at x is equal to 0 is T1, and temperature at x is equal to L is T2. Okay, which means it is going to start here and it is going to end here. So this is the starting and ending point. This is the starting point. This is the ending point for the temperature distribution. But the question is, how it is going to go from here to here. So for, as you said, it will be linear for a equal to 0. But I wanted to know, how did you come to that conclusion, or how we can come to any conclusion. So what is the way that we can find out how the temperature varies um, along a direction? So we can, any idea? So we have to use these informations. So if you have any ideas, please let me know.
Sir, according to Fourier's law, temperature difference will directly proportional to the length.
Temperature difference is directly proportional to the length. Okay.
Change in length.
Okay. So let's write down Fourier's
So,
law. Okay, it's partially right. Let me write down the Fourier's law. This is nothing but k into, let's say, as you said, we can write it in terms of delta t and delta x. Okay, but I wanted to know how t at, let's say, at some x1, some x2, any x, I wanted to know how the temperature is. That is the question, right? So as you said, delta t is proportional to delta x provided other things are in place. That is right.
and
But
negative sign.
so probably you are telling it should be like negative. Okay, but this doesn't really tell how I can go from here to here, right? But your thought process is right. We should use Fourier law of heat conduction, because only heat flux is given, heat flux is constant, and temperature profile we need to find out, which means we need to use Fourier's law of heat conduction. But since we need to know all the points are, we need to know the distribution, we cannot write it in terms of delta t and delta x. We have to write it in terms of differential equation. And then we need to solve the differential equation in order to get the distribution, because differential equation represents how a variable varies with respect to every point, with respect to each and every point, which is exactly what we need. We need to know temperature with respect to all x points, or for all the points within 0 to L. Okay, so then let's write down Fourier law in terms of dt, like general Fourier law for heat flux. It is written as q double prime x is minus k dt by dx. Okay, now I can take two approaches here. Okay, one is intuitive approach. We just think how the heat flows, and based on that you can guess the profile how it will look. The other one is you can take a rigorous mathematical approach. Okay, that also you can do to find out how temperature profile varies. Okay, so first I will show you the rigorous mathematical approach, because you know uh, and then we will try to find the insights from it, and it will be very easy if you could, if you could, without going through all the mathematics, with just basic intuition of how heat transfer works, you can actually predict how the profile varies. Okay, so let me show you a mathematical way. So now we have heat flux to be minus k dt by dx, and what we know, heat flux is constant, right? If the heat flux is constant, okay, now what we can also write is, if something is constant, its variation along x is equal to 0. We can write it like this, right? Tq double prime x by dx is 0. uh, Either you can directly write it, or you can take it from the heat equation that we derived. Okay, but we know it's since heat flux is a constant, its derivative is going to be 0, right? If this is the case, let's say if I substitute the Fourier law of heat conduction inside it, what happens? D by dx of minus k dt by dx. And if a is 0, this is equal to 0. This is true for any case. Now if a is 0, k is equal to k naught. If that is the case, the equation becomes d by dx of minus k naught dt by dx. And this k naught is a constant. It is not a function of x, or it is not a function of temperature. Okay, now if this is the case, what we can write, we can actually take this k naught out, k naught into d by dx of dt by dx. So it is, so this is just the derivative of first derivative of temperature, which is just a second derivative, and this k naught you can just take it to other side and you can make it 0. So this ultimately boils down to d square t by dx square equal to 0. Okay, so now the question comes, we know that this is the equation for temperature. Okay, you can solve this temperature equation. It's a differential equation, right? You can solve it subject to some boundary condition. Here the boundary condition would be T1 and T2. You can use this in order to solve it, and if you solve it, you will end up having linear equation for temperature. Let's try that. Let me do that for you. So we have d, then you can integrate it to get C1, and then you can write T is equal to C1x plus C2, right? This is basic mathematics. I hope you can understand this. So this is nothing but a form of y equal to mx plus c, right? So which is a line, and we know that at x is equal to 0, t is equal to t1, and at x is equal to L, t is equal to t2. Now what happens? Let's say if I substitute here, if I put x is equal to 0, t will be simply t1 will be equal to c2, and if I put x is equal to L, so probably I'll move this here. So if you just substitute this, what happens? T1 is equal to C2, okay, which means C2 is equal to T1. And if you do the other thing, C2 is equal to C1 times L plus C2, which is equal to C1 times L plus T1. Okay, in this way you can get C1 to be T2 minus T1 by L. Okay, now you can write the temperature to be, this is the temperature distribution. Temperature is a function of X. This temperature will be T2 minus T1 times L times X plus T1. So this is how, so you can see T is a function of temperature. So, T is a function of X, while the function we just found out based on based on this governing equation. In this case, this is the governing equation, okay, and subject to boundary condition. When you have a governing equation subject to proper boundary condition, you can actually find out the what do you call, the temperature distribution along the X. Okay, so once you find the temperature distribution, you can just simply plot it, okay, by varying X. If X is equal to L, your temperature, if X is equal to L by 2, let's say, what happens, you will just put L by 2 here. L by 2, L cancels, and then this becomes T2 by 2 minus T1 by 2 plus T1, which will be T2 plus T1 by 2, which is nothing but mean of these two, which will come in the midpoint. So basically, if it is L by 2 over here, it comes in the midpoint over here. And you can, draw these three lines and you can write it's a straight line. Basically, you can do this for, you can do this for every point in this line. And then you can just plot them and see how it varies. Okay, so in this case, what happened was this is a linear line, and we also found out it's a equation for line. So this is how you will find out that the temperature distribution or the shape. Now I will tell you, instead of going through all this mathematics, you can simply, use your logic to find out the same thing. Okay, so this is the line. Let me write it down. This is the line for A equal to 0. Okay, which means we have a constant thermal conductivity, and we know that it's going to give a linear profile, and this is what exactly we got after doing all the mathematics. Okay, you can repeat the similar mathematics for A greater than 0, A less than 0, and you can apply logics and you can find it. But now I'm going to give you a more easier way to do this. Okay, um, we can just, once you know this, this itself has the idea of how the temperature profile varies. Okay, so what I said here is you have heat flux which is constant. um, before we go into, is there any problem with the mathematics that I derived till now? I hope everything is clear. How did we got the temperature and how did we get it's a straight line? Everything, I hope it's clear. Okay, so if there are doubts, please stop me anytime and I would be happy to repeat it. Okay, now we have this heat flux equation. Okay, the heat flux is constant. Okay, which means it will not vary with X. That is number one. So that is number one clue for you to find out how this temperature profile will vary. Okay, so which means whatever the X you take, the heat flux will remain constant. Okay, now let's look at this form, which means this also should remain constant. Minus k dt by dx should also remain constant. Okay, now when A equal to 0, what happened? Let me write down the thought process so it will be easy for you. So now, initially what did I say? Heat flux is minus k dt by dx. Now I said this is constant. And this is Fourier's law of heat conduction, which is valid, which means this is constant, right? So there's no problem till now. And when A equal to 0, we know K is equal to K naught, and K naught is also constant. Okay, K naught is also constant. Now, if this is constant, what should be this? Will this be also constant? Right? This also should be constant.
Constant.
Right. You only if these two are constant, then this whole term as a whole will be constant, and if that is constant, then heat flux will be constant. Okay. And when will the temperature gradient be constant? What does temperature gradient being constant means? Temperature varies linearly. That's all. So simple. Which means you should know where it starts, you should know where it ends. Once you know where it starts and ends, you can close your eyes and draw a line. That's all. Which means it varies linearly. Okay, which means the temperature gradient is, so whether you find gradient here, or whether you find the gradient here, or whether you find the gradient here, everywhere the gradient is constant. That is what a line means. That is what for a line the slope is constant. Here the slope is temperature gradient, and hence it will be constant. Okay, so based on some mathematical understanding of how the graph varies, you can, and also what is the equation we have in hand, we can simply say this is a straight line. Okay, is that clear how the logic came? I hope it's clear for everyone.
Yes.
Okay, thank you, Basant, Chena. Now let's extend it, let's try to extend this logic. Let's not go through this detailed mathematical process, but I welcome you to do a detailed mathematical process and find out what is the, how would the temperature vary. Okay, so now let's do case 2, which is A, let's say positive. Okay, A is positive, which means K will be K naught plus AT, and as temperature increases, the K naught increases. So as T increases, K increases. The total thermal conductivity actually increases, continuously increases. Now let's do the same logic. Let's see whether you are able to understand this. Minus K dt by dx is the same logic. Um, so changing thermal conductivity will not change the heat flux. Heat flux is something coming from outside, and it's a steady state condition. Okay, so whatever heat flux it has to go through, so which means heat flux is always constant, so that you can say for sure. Okay, now heat flux is constant. If heat flux is constant, the right hand side is constant. Okay, now the question is, now K increases with X. Okay, so now okay, one thing along X, so how temperature, does temperature increase or decrease along X? Let's try to understand this question. So as X increases, as X goes from 0 to L, temperature goes from T1 to T2, which means temperature continuously decreases. Okay, now let's write that down. So T decreases along X as X increases, or along the positive X axis, along positive X, the T continuously decreases. Okay, now how does K vary? If T decreases, what happens to K? You can substitute in this equation. This T is continuously going to decrease, which means how the K will behave? K will also continuously decreases, right? Decreases along positive X. Okay, because this is just the equation. If T continuously decreases, if T decreases, K will decrease, because K naught and A are constants. It's not varying. Even though A is, positive, when A is positive, K naught is going to continuously decrease along positive x. Okay. Now now the question is, how does dt by dx varies along positive x? Now let's try to find out what is here. The k here is decreasing with x, and now if you want to make this whole term constant, what you have to do, you have to increase the temperature gradient. Okay, because one quantity is decreasing, which means other quantity should make it increase, so that both will cancel out each other and we will give a constant heat flux. Okay, so constant heat flux is true. That's why if k decreases along x, the dt by dx should increase along x. Because then only it will satisfy Fourier law of heat conduction. Is that clear?
Yes, sir. Yes, sir.
Okay. Now
Yeah.
if dt by dx increases along x, which means gradient is also changing, which means slope is also changing, right? If the slope increases along x, how we will draw this line? You think mathematically, you will find the answer for this.
I think it should be uphill.
It should be
Uphill.
right. Wonderful. So again, it should start from here. It should end at T2. There is no change in that. The boundary condition is fixed. Only thing is, it will look something like this. That's it. This will be A greater than 0. Okay. So what I'm saying is, delta T continuously increases. Our gradient is continuously increases. That is what you see here. The gradient here is less. The gradient here is very less. However, the gradient here is very large. Okay, which means the gradient, as the temperature, as you go from along the positive x, the gradient is continuously increasing. Okay, so let's say if I want to draw how the gradient varies along the x, this is another graph. This is x, this is dt by dx. Actually, gradient is negative, so this is x. So this is for a equal to 0, and when delta t increases, dt by dx continuously increases. Okay, and it is increases in the negative direction. That is something you need to note. It increases in the negative direction. This is for a greater than 0. Okay, initially you have very low negative delta t, and finally you will have very high negative temperature gradient. This is what a greater than 0 looks like. Okay, I hope this is clear. I didn't confuse you at all. If you have any questions, please stop by.
Could you please repeat it again, sir?
Okay, which one? This one, the temperature gradient
Yeah, yeah, yeah. Temperature gradient.
is the same thing. Okay, so now let's go back here. So the temperature gradient here, this is the gradient, right? So the delta t, this delta t by delta x, this is the temperature gradient. Okay, this gradient is very small here, and the gradient here is very large. Sorry, the gradient here is very large. So there is a large delta t for a very small x. There is a large delta t for a very small x. However, here there is a small delta t for a large x, which
Yes,
means
sir. Yes.
which
Yes,
means
sir.
the dt by dx is small here, but also it's negative. That's why I plotted in the negative uh, direction. The plot is something like this, in the negative direction. Okay,
Mm-hmm.
right, in the fourth quadrant you will have very small you know gradient over in your x is equal to 0. However, you will have a very large gradient at x is equal to L. Okay, this corresponds to a very large gradient. That is why
Yes,
you
sir.
will have a gradient to be decreasing. And one more thing, actually This no need to be straight line. It could be something like this also, it could be something like that also. However it can be, but it should continuously decrease. That is what we don't know exactly how the delta dt by dx, uh, how it is a function of x, we don't know. Okay, so but only thing is it strictly decreases, sorry, strictly increases in the negative direction. Okay, all right, so that is how you got this profile. This is for a greater than
Greater
0.
than 0.
Now you guys can directly say how okay a less than 0 would be. It's going to be just opposite of this, but
Yeah.
you can repeat this same analysis and I mean same thought process, and you can see for yourself how it will vary. So it is going to vary as you suspected. It's going to vary something like this.
Sir, all these recording will be available to us?
Yeah, it will be available, don't worry
Okay,
about
sir.
it.
Okay, sir. Thank you. Thank you.
But if you have doubts, don't feel shy. I will
Okay.
be happy to explain you
Yeah, yeah,
multiple
yeah.
times. Okay.
Once we have to do it once again
Okay.
ourselves,
No problem. No
it will
problem.
be helpful.
Okay. No problem.
Right.
So, and this is the second approach. This is the easiest way, just based on thinking, you can find out how it will vary. The other approach is you can do this derivation again, and you can come up with this expression. Okay. Again, and you can plot that, and only when you plot it, let's say using a software, or let's say MATLAB or Excel sheets, if you want, if you're plotting it, then you will come to know it also varies like this. So it's a very far-fetched process. Instead you can just simply use uh, intuitive approach, and you can find it. All right, I hope question 3, I skipped few parts. A negative, a less than 0, I didn't do it, but I hope you understand the gist, and you can do it on your own. All right. All right. So I thought I will be able to finish this by 8, but uh, probably it's taking some more time. We'll quickly go through these 2 questions, and then I will leave it up to you guys to ask any questions. Okay. So the fourth question is a little bit different, which we didn't touch in the lecture, because it's in like kind of a cylindrical coordinate. Till now we studied only uh, Cartesian coordinates. Now we are going to do cylindrical coordinates. Here what we are talking about is a hot water pipe with outer radius r1. Yeah, there's a pipe, and the hot water is flowing through it. It has outer radius r1 and has a temperature T1. And now we are applying some thick insulation. A thick insulation applied to reduce the heat loss. So when you apply insulation, the heat loss reduces. As an outer radius of R2 and temperature T2. Okay, so let me draw it. So you have this hot water pipe with radius R1, and you have a bigger insulation with radius R2. Ideally, it should be in the middle. All right. So now this is R1, or maybe this is R1, this is R2. So this is the insulation. Or probably you might think that it is water. Sorry for the color choice. But this is the insulation. Okay. Now this is at T1 and this is at T2. Now what they are telling is, on TR coordinates, sketch the temperature distribution in the insulation for one dimension. Steady state heat transfer. You can assume steady state, constant properties, and one dimensional. Give a brief explanation justifying the shape of your curve. What would be the temperature distribution will be if you were along the R direction. Okay, so let's say this is the direction you are going for. How would the temperature vary? Basically, in the previous problem, we studied how temperature varies along the x direction. Here we are trying to find out how it varies along the r direction. And we say it's one dimension because it's one dimension along the radial direction. So at every radius you will have same temperature. That's what it means. So this is one radius, this is another radius. So as you go outer and outer, every radius you will have one temperature. I mean, it will be iso, what do you call it? Thermal along a radius, along each radius. Okay. All right. Um, Again, it's a steady state heat transfer. So we have heat flux to be constant along the radial direction. That is one difference. So let's say if we do that, heat flux is equal to constant, or in this case, I'm going to write it in terms of heat, not the heat flux. Okay, the heat is constant. So we will understand why. Okay, so there is this water flowing over here. There is this water flowing and it is hot, and the ambient temperature is cold. So there is going to be a temperature. There's a potential. So the heat flows from hot water pipe to outside, but in between it sees an insulation. So a less amount of heat passes through, but it doesn't mean the heat does not pass through at all. So there's going to be some heat loss to the surroundings. Now, when you have heat loss to the surroundings, along the r direction, the heat will be constant. Okay. Um, uh, we will see how the heat flux varies. Okay, first let's understand if heat is constant, we can apply Fourier's law. Fourier's law, again it is same, k times area times dt by dr. Here it is in terms of radial coordinate. Now the question to you guys is, what is this a? How will you write the a? So we all know a is the
Surface area.
which surface area?
This is the internal surface area. That
uh,
is,
yeah, I mean, you're partially right. It's for any radial direction.
that
What
is
will be the circumferential, you know?
circumference multiplied with length.
Right, exactly. So as you said, a will be, there will be perimeter, which is 2 pi r
Perimeter into length.
times L. So because
Yeah.
this is in the z direction, it extends in L. Okay, that will be the area. So you can see, let's say this is your any arbitrary radius, the heat is going perpendicular to it. So perpendicular to it, what is the area it sees? It sees a 2 pi r times L. So that is the cylinder it sees. Okay, so that's why we choose this area. I hope it's clear for everyone. So if that is the case, we can write this QR to be minus k into 2 pi r L times dt by dr. Okay, now we know that this is going to be constant. So, and also 2 pi and L we are going to take to be constant. So this actually boils down to r times r. Maybe I will write down the equations. Minus k 2 pi L times r into dt by dr is equal to constant. And I can club all the constants. These are also constants. So I can club all the constants and I can write the equation to be r times dt by dr is equal to some constant. Maybe I will call it C1. So this is what the Fourier law of heat conduction along the cylindrical coordinate says. Now from here we need to find out, so our goal is to find out how T varies with respect to R. This is our goal, how it varies. So similarly we need to draw a graph and we need to show, let's say if I draw it in a graph, this is radial coordinate, this is temperature. I wanted to know how it varies along R. So which means, let's say I'm going from R1 to R2, and I know that at R1 I have T1 and it's a hot water, so T1 is going to be greater than T2. Okay, so at R1 you have very high temperature and at R2 you have low temperature, which means, let's say if I extend this line and extend this line and extend this line, my starting point is going to be here and I'm going to go here. Now again the problem is how this T is going to vary in between R1 and R. That is the problem. What is this T? It's a function of R, is the question that they are asking. And for that we have a solution. We have R times dt by dr to be constant. Okay, so now you can apply your mathematical, you can rigorously derive it, and you can express the solution, or you can apply some logics and you can tell me how it varies. Do you guys have any idea? You can apply the same logic. So maybe let me help you here. So you have dt by dr to be equal to C1 by R. Okay, so now your temperature gradient. So temperature gradient along radial direction is also a function of radius. Okay, now it is going to vary with respect to 1 by R, which means as R increases, temperature gradient reduces. Okay, now which means the temperature gradient is going to be more when R is equal to R1, and the temperature gradient going to be less when R is equal to R2. Okay, so based on this logic, we can actually draw this line. So the gradient is going to be more, which means it's going to steeply drop at R1, and the gradient is going to be less when as it reaches R2, because R2 is larger. It's going to be less, so it is going to be the gradient is going to be small near the R2. So which means what I'm trying to say is it is steeply dropping. Okay, steeply dropping, and then as it goes down, the temperature gradient continuously reduces and reduces to a very low value at the end. So that's what it means. Basically, this is kind of like a, what is this?
Going down a hill, no? Very
Right.
steep hill.
Yeah. Yeah. So this is the profile. Okay. Maybe I will exaggerate some more. Yeah. So as I said, the temperature gradient is large here. However, temperature gradient is small here. Okay, which means like the changes in temperature with respect to small variation of x is very large. That's what temperature gradient large means, and that is a function of radius, and this radius is in denominator. That's the thing. If the radius is small, temperature gradient is large. If the radius is large, temperature gradient is small. So that's what you see. The radius is small over here, that's why you have large temperature gradient, and as you go along the radius you will have small temperature gradient. Okay, now this is one way you can, based on logic, you can do. The more rigorous way, you continue this. You can write this as dt is equal to C1 times dr by r, and you can integrate it. When you integrate, what happens? T is equal to C1 times logarithm of r plus C2. Okay, and we know the boundary conditions. What are the boundary conditions? At r equal to r1, t is equal to t1, and at r equal to r2, t is equal to t2. Now you apply this boundary condition, and you can get the temperature profile. You can plot them in Excel or wherever you want, and then what you see is it is going to vary something like this. It is going to vary something like this. Okay, so these are some important understanding that you need to have. The way you try to perceive this problem will be very helpful. Let's say if you are going into an interview, or if you are going to, let's say, write a gate exam also, these kinds of questions will be a lot. Okay, so how the temperature profile varies, how this works. So at that time, a proper way of analyzing these concepts would be very helpful rather than deriving this mathematical relation. And we do not have access to plotting softwares and all while we are in time crunch like interview or exams. At that time, this idea of how the mathematical graphs vary, the calculus idea of calculus, and the understanding of temperature gradient and the profiles will help you in uh, get a rough estimate of how things vary. Okay, so you try to practice these kinds of problems if you get a chance, and all these problems I usually take it from heat and mass transfer in Cropera book. So which I find it to be important and necessary to discuss those problems I usually pick for you to show. So you can find similar problems a lot in Cropera. It would be
Sir,
very
what is the
helpful
name
for
of
you.
the book, sir? Excuse me.
It's
What
a
is the-
it's a heat and mass transfer by fundamentals of heat and mass transfer by uh, in Cropera. In Cropera. If you it's a famous book in heat and mass transfer. It's one of the suggested books for this course also. Okay, I think it's fundamentals of heat and mass transfer.
Okay, thank you, sir. Thank you.
Okay, so you can get it. I will also, if I get a snapshot of uh, first page of the book, I will add it in this PDF and I will upload so that you can find out from there also. All right. Any questions? Any questions till now? I think it went suddenly it went into mathematics and calculus, and it might be a little bit boring, but it's good to understand these concepts. So I hope there is no question. So we are already 8:20. Anyway, session is still 9 o'clock. Um, what I will do is in another quickly in 10 minutes I will quickly go through this problem. If possible, I will complete it or I will let you to complete. It is straightforward, but some important insights I will give you. Based on that, you can complete on your own. Okay. Um, so this problem actually involves a little bit about energy balance. Uh, so Professor Suman Chakraborty was very nicely explaining about money balance, and then he directly converts that into energy balance. If you haven't seen that video, I strongly recommend you to look at it. um, I think it's the fourth or fifth lecture of this week. So um, we are going to use that concepts a little bit, and that concept is very powerful. You can use it anywhere, and you can arrive at the solution. Okay. um, it gives you a lot of insights. Okay, so let's see how we are going to use that here. Consider a surface mount type transistor on a circuit board whose temperature is maintained at 35 degrees Celsius. Okay, air at 20 degrees Celsius flow over the upper surface of the upper surface of this transistor with the dimension of this and a convection coefficient of 50 watts per meter Kelvin. So which means like you have this is the circuit board. This gray part is a circuit board, and on top of it you have this transistor, or you can say IC. Any chip you have this chip over here, and there is a air flowing all on the chip with a and the convection coefficient or heat transfer coefficient over that is watt per 50 watt per meter Kelvin. Now what they are telling is there is a three wires coming out of this transistor and it goes to this circuit board. Okay, and these three wires has some cross section and some length. Okay, and they conduct heat. So you should note here they conduct heat from the case to the circuit board. So this is this transistor case. Okay, from transistor case to circuit board they have these wires. These wires, in addition to electrical signals, it also conducts heat, and uh, it conducts heat with some thermal conductivity which is also given. Okay, um, the gap between the case So between the case and the circuit board is 0.2 mm. Okay, assuming case is isothermal, no radiation, let's ignore radiation for a moment, and estimate the case temperature when 150 milliwatt of is dissipated by the transistor, which means this is a transistor, and when there is a electrical signal given, or when there is a voltage given, power given to this transistor is going to generate heat, and the heat generated over here is 150 milliwatt, and whatever heat is generated, it is getting conducted through this wire to the board. It is also getting convected by the air, and also it is getting convected by the air in this small gap. So there are like three kinds of heat transfer. Okay, so one thing is it is getting conducted along the wire, it is getting convected by the top surface, convected by the air by top surface, and also it is getting dissipated by the transistor from the stagnant air, you know, at the bottom. When you say here the stagnant air, it is not as same as convection. Here it is also conduction. That is something you need to remember. Okay, so if you have a stagnant air, that is how um, that is also one way of heat transfer happening over here, and you have a conduction through this wire, and you have a convection on top surface. Okay, now what they are trying to find out is what would be the temperature of this case. That is what they are finding. What would be the temperature of this case? Now we are assuming it to be isothermal, which means the entire case is at same temperature. Okay, that is another simplification. In reality it will not be. The temperatures will be continually varying in all these points. Okay, temperature, there will be a distribution. Okay, um, but we are going to assume it's a isothermal, and if we say it's an isothermal, we just need to find out one temperature, which is Tc. What is this Tc is what they are trying to find out, what we are trying to find out. Now what they are telling is, now I have this gap. This gap, if I, let's say I leave it like this, let's say only air is present. If air is present, what would be the temperature of this case? Let's say I do not have air, instead I am filling it with a conductive paste. So there is something called thermal paste, which people usually do, uh, you know, apply on the top of the uh, IC chips. For example, if you have a system in your system, you have this Intel chips, right? Let's say if you have an Intel processors, you have this processor chips. On top of the processor, you will see a heat sink. There will be like aluminum, uh, uh, you know, aluminum heat sink, which will be like fins, like a lot of fins arranged in a square section. Okay, so this aluminum heat sink will be there. In between aluminum heat sink and the processor, there will be a conductive thermal paste that they usually apply. Nowadays, people are coming up with liquid cooled engines, liquid cooled computers, but in, you know, in general purpose computers, you can see there will be a processor and there will be a thermal paste applied, and on top of it there will be heat sink. Here is some similar case. You have some gap in between the circuit board and the transistor. Here you are applying, let's say, some conductive paste. If you are applying with some thermal conductivity, how would that enhance the heat transfer is what they are asking, which means how would that reduce the temperature of the transistor. We basically want the processor or the transistor's temperature to be less. Okay, as so if the temperature of this transistor is less, the computer performs very efficiently. If it becomes very hot, it starts misbehaving or sometimes breaks down also. That's why it's important to control the temperature of the processor. Okay, um, that is the background. So basically we need to find out, let's say if all these heat transfer process happens, what will be my uh, temperature on of the case is the question that we have. Okay, so now how do we approach this problem?
So actually, uh, we have to use the energy balance equation. That is
Correct.
uh, being coming in plus generated minus heat
Energy out,
energy out.
right?
So that is equal to the rate of heat
Energy
transfer
stored, right?
stored. Exactly.
Right, exactly. Wonderful. So that is exactly is what I wanted to say. So these kinds of problems which requires multiple heat transfers, heat exchanges, what you have to do is something called energy balance, which is what we discussed in the lecture, right? So we started with money balance and then we did energy balance. Okay, so which means energy can neither be created or destroyed, which means energy can go from one form to other form, or it can go uh, it can move from one place to other place. That is what this whole heat transfer is about. So just by doing energy balance you can uh, try to understand this thing. Now before we do energy balance, we should do one important thing. We should do something called uh, control volume. We should draw a system, or we should draw a control volume, and for a control volume you have to do energy balance. You cannot do energy balance like that. Okay, so important thing is we have to draw something called control volume. In this case, only based on, so only if you base your uh, heat transfer analysis for a certain object, only when you restrict to a certain object, you will be able to resolve what and all heat is, whether heat is coming in or going out. When you say it is coming in, it is going out, you have to refer it to certain object. So it is coming in through a room, it is going out of the room, right? So this room is a control volume. Similarly here, we are going to take control volume as a transistor, because our main interest, our main goal is to find the temperature of the transistor. So in that way, let's say the system of our study, or the uh, area or the interest of the study here is transistor, and that's why we should take the control volume to be the transistor. Okay, or the system to be our transistor. Now let's, if when I say it's a transistor, what it means is this this thing that I have here, I'm going to draw it in dotted line, which includes wire also. Okay, or no, sorry, we are interested in only transistor, we do not need wire. So we want only case temperature, right? So we will base our area of study only on the transistor. Okay, if that is the case, now you can write as Basant Jana said, you can write the energy balance to be, you can write the energy balance E dot in minus E dot out plus E dot generation is equal to E dot stored. Okay, basically whatever comes in minus goes out plus whatever is generated will be the change in energy of that system, or the energy stored, or rate of change of energy within the control volume. All are same, E dot stored. Now uh, this rate of change of energy within a control volume will be present only if it is a unsteady problem. Okay, so here we are going to deal with a steady state thing, so we do not have this term. Okay, so basically what I'm trying to say is this transistor's energy does not vary with time. It generates and it dissipates to different modes like conduction and convection. It dissipates is what I'm trying to say. Whatever it is generated, it is getting dissipated. Then only you will have uh, temperature to be not a function of time. Then only you will have a steady state uh, uh, you know system. Okay, so that is what we are going to do. We are going to assume it's a steady state system. Okay, and also you are also telling case is isothermal. Okay, which means the temperature does not vary within the case. Okay, temperature is, it's a single temperature. It is everywhere it's the same temperature. That's what it means. Okay, so now this actually boils down to um, E dot in minus E dot out plus E dot generation is equal to 0. Okay. Now, do we have any heat? So we need to find out what is this E dot in, E dot out, and E dot generation based on this. Okay. So do we have any energy coming into the transistor in terms of heat? Here we are interested in heat. Is there any energy coming into the transistor? So you can understand this transistor is generating heat and it is dissipating heat, which means it is sending out all the heat, okay, through the conduction through wires, through the convection of air at the top surface, and also conduction at the bottom surface.
I
So
think there is no energy coming in.
exactly, right. So we do not have any energy which is coming in. So we do not
Yeah,
have any external energy coming in. So here when you say E dot in, it has to cross the boundary of the control volume. Okay. So there is no, the energy should cross and get into the system. So that is not happening. Only energy is going out of the system through wires, to through the convection by air, through the stagnant air below. Okay. Only energy is going out. Energy is not coming in. If these are, across the control volume, it has to, from external it has to enter. Okay. So in that way, the E dot in is actually 0. And what are the E outs? We have a lot of E outs, right? One form is through the wire we have Q conduction going out. Okay. uh, Sorry.
there is three mode of energy out.
Right, right.
Three
So
mode.
three modes of energy out, that
Yeah,
is
yeah.
correct. Wonderful. So you have Q wire. In fact, I will say wires, because we have three wires going out. So you have Q wires, which is a conduction, and you have Q air at the top surface, which is a convection. Okay, let me write it as top. Okay, and what you also have is Q air, but it is stagnant. If it is stagnant, if the air is
So
not
that
flowing,
will be considered as conduction. That will be considered as conduction.
right, wonderful, this will be considered conduction. Now what you have to do, conduction we know it's Fourier law of heat conduction, convection we know it's Newton's law of cooling. You just need to substitute those expressions. That will be our E dot out. Okay, let me write one more step in this. So we have three wires, so we need to multiply 3 to it. So it's 3 times Q conduction of one wire would be minus K area of the cross section of the wire times dt by dx, or you can write it as delta t by delta x. Now important thing is, what is this area, what is this delta t is the important thing. Okay, we will come to that. And this is one thing. And the Q convection is Newton's law of cooling. Area of the surface, top surface of the uh, you know the case, and then T case minus T infinity. This is Newton's law of cooling. And bottom you have stagnant air. This is the bottom. This is actually, how do you write? So this is the bottom surface you have. Here the stagnant air is there, through which the conduction goes to the circuit board. Okay, this is the gray area, it goes to the circuit board. So which means you will have another minus K. Here it will be airs, and again here it will be wire. So K air, and surface area at the bottom, let me write SB here, ST, times delta T by delta X. Okay, all right. Now the question is, what is this area of cross section of the wire? Which area would that be? So here we see from the equation, so sorry, from the problem statement, you have three wire leads, each of cross section 1 mm cross 0.25 mm, and the length is 4 mm. Okay, so the cross section means this is the cross section. That part is the cross section, and across this the wire goes down. Okay, the wire length is, this wire is 4 mm, and the cross section here is the 1 mm cross 0.5 mm. Okay, so please be careful. This is 1 mm cross 0.5 mm. Okay, and the length is 4 mm, which is going to be your delta x. This is going to be 4 mm. Now the delta T would be, what would be the delta T? This is the circuit board, so the board temperature is also given. T board is, circuit board is 35 degrees Celsius. 35 degrees Celsius, and you have T infinity. T infinity is 20 degrees Celsius. That's also given. Now what you see, okay, let me draw this wire separately so that you will get an understanding.
I think there is some mistake, sir. I think there is some mistake. I think the cross section is. Uh, can you could you please sir show me
Oh,
the
0.25.
point two
Okay,
exactly point two.
yeah, thank you, sorry about that. um this 0.25. Thank you very much. So now if you have the wire, okay, this is the wire, this is the wire. So this area I'm talking is the area of cross section. Okay, and here the temperature is Tc. This is the case temperature. As I said, it's a uniform, whether it's top or bottom doesn't matter, where it just case temperature. And the bottom that you have here is at Tb. Okay, this temperature is at Tb. Okay, and the distance, the length of this wire along this curved path is 4 mm. Okay, and across this only conduction is happening. The conduction is happening like this, Q conduction. Okay, I hope it's clear when you draw it in a bigger thing.
Yes, yes, yes.
Okay, now you can find what is delta T. Now the delta T would be, what would be this delta T? This delta T would be TB minus TC. Okay, so this one will be TB minus TC. Now TB would be lower, TC would be higher, so this will be negative, but you have another negative in this will be negative, but you have another negative in front of you, so it will be positive, which means Q is going out. Okay, so we are adding everything in the E dot out. Q is going out. Okay, all right, I hope it's clear. Now now for convection it should be a little bit easier. So air is going on top surface of this case. So whatever the case surface, upper surface dimension is given, 4 mm cross 8 mm will be the surface area across which convection is happening. Okay, so this would be 4 mm cross 8 mm, and otherwise we know h is given, that is also fine. Now we have bottom surface of the gap, sorry, bottom surface of this case and the gap. So this is where the conduction is happening. Let's say if I want to draw this separately. Okay, so this is the gap, 0.2 mm, and here the temperature is T case, and here the temperature is T base or the circuit board. Okay, on top of it you have uh, the transistor. This is where you have the transistor. I'm just drawing the the stagnant air. So this is filled with stagnant air. And the heat flux is actually flowing in the downward direction. This is the Q conduction of the air. Okay, heat flux is going in the downward direction to the circuit board temperature. So that is what you need to write it down over here. So this would be this surface area. This surface area is going to be same as top surface area if you consider it to be rectangle, which we will do for this problem. Then it becomes again 4 mm cross 8 mm. Now the delta x would be the gap. Okay, I hope you understand. This delta x would be this 0.2 mm, and this delta t would be same as TB minus TC. Okay. This would be same as TB minus TC. Okay. Okay, so for better clarity, I will write one more time down. So the E dot out is equal to 3 times minus KA wire 1 mm cross 0.25 mm, that is the area, times TB minus TC divided by 4 mm, that is the length of the wire, plus H of the air. Area here is 4 mm cross 8 mm times Tc minus T infinity plus minus of K air times 4 mm cross 8 mm, which is the area of the stagnant air, times TB minus TC divided by 0.2 mm. Okay, so other things I'm not substituting because those are given already in the uh, problem statement. You can just simply substitute it. Okay, this is the E out. Okay, you can find the E out in terms of TC. All right, so E out is done now. So E in is 0. So E out is done. Now E dot generation. E dot generation is 150 milliwatt. That is also given. Okay. E dot generation is 150 milli. So it will be 10 power minus 3 watts. Okay. Now what you have to do, E dot in is 0. So minus E dot out plus E dot generation is equal to 0, which means you just need to equate E dot out is equal to E dot generation. Okay, E dot generation we already know. Okay,
Yeah, yeah.
you just substitute them here, and then you will, here we know everything. We know K wire, we know TC we need to find, T base 35 degrees Celsius we know, H we know, I think it's 50 watt per meter square Kelvin, and T infinity is 20 degrees Celsius, and here also T base we know, K R we know, everything we know except TC. Okay, here we don't know TC, here we don't know TC, here E dot generation is 150 milliwatt. You equate these two, you will end up having TC. Okay, so I'm not solving here, probably I will give you the answer here. So when you use air as a stagnant, so there is a gap, so if that is filled with stagnant air, you will have a temperature of, I think, how much did I get? 47 degrees Celsius. Okay, you can check for yourself. And what also they were asking is Let's say if I replace that stagnant air with the conductive paste, okay, if I replace that with the thermal paste, as I said, then I will have a different thermal conductivity. So wire leads air and conductive paste thermal conductivity is 0.212. However, air's thermal conductivity is 0.026, which means you are going to conduct more heat. The thermal conductivity increases, the the conductive heat across this gap is going to be increased. If that increases, your temperature is going to, when you have paste, what is going to happen to the temperature if the conductive material, if you change the material to high conductivity material, what is going to happen to your temperature?
It will reduce rapidly.
Right, it reduces. So actually when you use the paste, I was getting 39.9 degrees Celsius, but you can verify for yourself. Okay, so basically you just need to replace this Kr to K conductive paste. Okay, the 0.12. So when you replace that over here and again equate it to same 150, the generative heat is not varying, again equate it to same 150 milliwatts, you will end up having a lower uh, temperature, so that you can see for yourself. So that is why people, instead of just leaving it like that, they fill it with the thermal paste so that they can reduce the temperature of the transistor. Okay, so I have another question, but I think it is better discussed in the next week, because you will get additional information on this steady state heat conduction in the next week. So I'm going to reserve this question for the next week. Nevertheless, if you have any, I strongly encourage you to finish this problem 5. Try to think again. We know it was a little bit rushed, but think again how this energy balance is worked out and how the areas and temperatures and uh, you know the distances we are taking it into account. Uh, and also, I encourage you to do some mathematics in the third and fourth problem. That will help you. Otherwise, I think first and second is straightforward implementation, straightforward usage of Fourier's law of heat conduction and Newton law of cooling. I think that is more than sufficient for your assignment for that sake. All right. If you have any questions, I will be happy to take. And I'm sorry for taking you a longer time. Uh, if not, we will meet next week. Okay. I'm really hoping for you to come attend next week also.
Okay, thank you, sir.
Thank you,
Thank
Faisal.
you very much, sir.
Thank you. Thank you. Thanks for
Is
joining.
it, will it be available in the same platform, the recording?
Yeah, yeah. So I will upload this in the Google Drive. I will upload this notes in the Google Drive. I will also upload this recording in YouTube, and I will share the link, and that will be available in your Swayam portal. There will be
Oh,
separate problem solving session, uh, option in your portal. You can go and access. You can open the sheets, and you can get the access.
okay, sir. Thank you.
All right. Thank you very
Bye bye.
much. Yeah. Thank you, Venkatesh, Avinash, and Unanti also. I think Unanti Jain, you had some question. Uh,
Yes, sir. Once I will read this PDF, I'll get to know.
okay. So,
I
uh,
think there's conceptual issue, just missing of one equation in between.
okay, okay. So basically, yeah, while deriving, professor used some tedious equations and the Maxwell relations. So thermodynamics is, one of the prerequisite of this course. So there you will actually read this. Um, come up you come up with these tedious relations and the Maxwell relations. So uh, that when you substitute those, you will end up having, but you can physically understand. So it's nothing complicated. This is something like energy stored in the, in a material inside a control volume, and this is the heat flux entering and leaving. Okay, and it can also vary using heat generation. Now in addition, what happens is, if you have a liquid or other things, based on pressure also the amount of energy content varies, because our enthalpy is a function of both pressure and temperature, and that's the reason you will have this additional term. If not, you will not have. for gases, for for air, this volume expansivity, this beta, is actually 1 by T. Okay, so then you will have only dou P by dou T term. You will not have this beta and T. This beta will be present uh, for, if you use ideal gas, this beta will not be present. uh, this only dP by dt will be present, or dou P by dou T will be present. If you use liquids, let's say, then you will have a different expression for this. If you use solids, this term is generally zero. So there is no solid. We use it as a rigid solid. So based on energy, if the temperature varies, it does not vary the volume or things like that. That's why we take this to be zero. So in general, this is the equation. This part actually comes because of this, uh, because we write enthalpy to be function of both pressure and temperature, and we go through certain steps. Okay, you go through once again, and if you still have any questions, please let me know next time, and maybe we can derive it together, and we'll resolve your issues.
Yeah, sure. Thank you, sir.
Okay, sure.
So could you please show the equation you have derived?
No, this is
Yes,
the same equation that professor derived in the chapter, sorry, lecture 5.
sir.
So I just saw the lecture, and then I just wrote this equation. Nothing much. So
Okay, sir.
you
Thank
can
you.
check the lecture 5. Lecture
Yeah, yeah,
5
yeah.
also has the same equation. Yeah.
Right,
So
sir. Right, sir.
basically, I just saw the lecture, and then I followed the process, because this can be derived in different ways. Um, so I wanted to know how professor has derived, so that I will also follow the same thing while I'm doing this problem solving session, so that it will be easy for you to understand. That's the reason I I went through it, and then I derived this. You can also do the same thing, and if you still have any questions, anyway, we will be heavily dealing with this for the next week. So if most probably all your questions will be resolved in the next week.
So in Tuesday, next Tuesday, because there is another tutorial class in Tuesday.
The Tuesday we are going to again study this conduction only. We are not going to do the week 2 again. um, so we have like two tutors. One is me, the other one is one more student that you will meet on Tuesday. He will be solving the first week's content. He will also will be doing a first week content. Okay,
Okay, okay.
so only the next Saturday again I will be here. I'll be dealing with week 2, and the next Tuesday he will also will be dealing with week 2. So there will be like two tutors who will be dealing with the same subject, so that if one person, if you couldn't understand one person, you can still again go and get to the other person, and you can understand. But
Okay, okay.
it's just a two tutors dealing with the same subject, the same topics. Okay, so yeah, and also, but he will not be solving the same questions. I have a different question. I solve some 5 questions. He will be having different 5 questions, 5 or 10 questions he will be having, and he will be solving those questions. So it will not be repetitive. So you no need to worry.
Okay,
Okay.
sir. He'll be again from IIT Gandhara.
But the uh, 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 but the what do you call, the portions are same. The content is same for
Okay,
Tuesday.
okay.
Content week 1 content only he will be
Okay, right,
discussing.
sir.
We will not be discussing week 2 content.
Okay,
Week
right,
2
sir.
content I will be discussing on next Saturday. He will be discussing on next to next Tuesday
Right, sir. Right,
after
sir.
my
Understood.
session. Okay.
Sir, I want some suggestion from your side. It is about the course choose. Which course should I choose? If you
Mm-hmm.
don't mind, can
Mm-hmm.
I ask you?
Yeah, yeah, sure, sure.
So there are two courses in which I am confused. One is this conduction and convection. Second is CFD. So my aim is to work on multi-phase.
Mm-hmm. Okay. Uh, which program are you in currently?
Uh, Actually, I am new to this multi-phase,
Are you a
and
BTech student or a master's
yes, I am BTech student final year,
Oh, okay.
and yeah, so I am going through an internship.
Mm-hmm.
There I have to work on multi-phase. So I require knowledge. I don't know what topics will be required in multi-phase.
So do you do
So what about
computations
you?
or computation or like experimental work?
Um,
CFD, are you going to do CFD? So yeah, are you going to deal with this CFD kind of work,
yes.
or are you going to deal with experiments? Are you going to do experiments on multiphase?
Actually, I will be working on open form.
Okay,
So
okay. So
I
basically
don't basically
CFD.
know yeah, I don't know the path
Okay,
actually.
okay, okay. Um, so actually, this is a fundamental course. Heat transfer is a fundamental course. You must have studied already uh, in
Yes.
your second or third year. Um, So this is going to be covering the same course that you studied in your BTech in your second year. Okay, it is does not deal with any advanced level uh, topics. It will be only again going through all the heat conduction equation, 1D steady state heat conduction, and then with heat generation, fins, and convection, and internal convection, external convection, all the same whatever you studied in your heat transfer course. This is also going to deal with the same thing. Okay, it is not anything advanced, so it has kind of no relation with the multi-phase flows, because multi-phase flows is very advanced. It does not come in this it is out of scope of this course. Actually, it's a basic like undergraduate level heat transfer course that we typically see in any uh, universities or any institutes. Okay, and CFD is typically a postgraduate level course, and if you are dealing with a if you're going to do CFD simulations, taking a CFD course is very much important. You should take that, whether you are dealing with multi-phase flows or not, doesn't matter. At the end of the day, these are all flows, and you have to start with the single phase flows, and for the single phase flows, CFD is very and you are doing CFD simulations, then you have to understand the CFD concepts. So you should you should have some knowledge on CFD. You should take the CFD course. That is must if your focus is on you know performing a computational multi-phase flow kind of simulations. Okay. Uh,
Yes.
I think
Okay.
unfortunately we do not have computational multi-phase flow dynamics. I think it's only CFD. uh, Multi-phase flow dynamics kind of there are I think there are a few courses on multi-phase flows. You can enroll in that also if you are interested, if you wanted to know more about it, or mostly I think you have to go through some books on it, most probably. Uh, yeah but yeah, CFD is a CFD should be, you should take CFD if your path is in computational only.
Okay. Okay. Thank you, sir.
All right. um So, any other questions? We have Avinash and Venkatesh. If you have any questions, I'll be happy to take. Um, if not, thanks for attending, and we will again meet in the next week, Saturday. Okay, and also please do attend the Tuesday session also. It would be very
Thank you, sir.
helpful.
Thank you.
All
Thank
right.
you very much.
Thank you, Basanjana. Thank you, Avinash. Thank you, Nati. Thank you, Venkatesh. We will meet next week.
Thank you, sir. Thank you.
All right. Bye bye.
Bye bye.
Maybe.